All right, so ladies and gentlemen, welcome to day 4 of OSCC 2025, and we are excited to be here at about this time. So let's get our official welcome remarks from volunteer Mohammed. Mohammed, are you there?
Yes, I'm here.
Okay, you can go ahead.
Yeah, good evening, everyone. My name is Mohammad Hanan. I am a PhD scholar in Ohio University, China. It's truly inspiring to see you all from across the globe, united by one passion. We are welcome to OSCC 2025 Day 4. Today is about machine learning and the artificial intelligence. We would we would like to encourage you to participate actively, ask questions, and make the most of this gathering. Together, let us make today's session a memorable and impactful experience for everyone. So, thank you for being here, and once again, welcome.
Oh, okay, thank you so much. We have played this video on the first day, and the video is also on the website. So you can always go there and watch the video. Similar to the other one that will come up. But always the program, today is the 4, and we have 2 days to end this edition of the program. We'll be having 2 speakers today that will be speaking to us on what they have unique for us today. So our first speaker will be coming up shortly, and he's going to talk more about himself and also what he has for us today. And please always make sure to check your name on the Zoom platform and make sure the name that you have is your real name so that it don't affect the attendance. As you know, we don't just give out certificates to just anyone, but people who will meet the requirement of attending 5 of the 6 days or all of the 6 days. So in order for you to not miss that, please try to use your real name. The volunteers have experienced some problems with some people who haven't been able to use their real names. So on tomorrow, basically, we will try to launch the feedback, or maybe on the last day, we want to launch the feedback, and you can give us a feedback from the program, and it can help us to improve for the next edition. Some of you asked about admission process or application for scholarship in university in China. So we are recommending Ohio University to you. You can apply or probably encourage your friends to apply. Application fees is 400 renminbi, or that's the Chinese currency. Maybe in USD, it should be around maybe 50 or 60 USD. So you can prepare that when you are applying. The link is already there, so you can take it up yourself. You don't have to pay anyone to apply for you. So everything is there. Just take a screenshot of this page, and you can make further inquiries and learn more about every other thing they have. You can also share with your friends or in your network, your families, if you are not the one to be benefited. So we have also a couple of people joining from different places. And if you just joining us, just let us know in the comment section where you are joining us from. Let us know in the comment section where you are joining us from. And we have people from different disciplines, not just computer science people, but we also have just students joining. We also have people that are also into the technical field and in different areas as well. So let us know where you're joining us from in the chat session. We'll continue to further through with that. So by tomorrow, we'll start up with the preparation of the certificates for the volunteers, the speakers, and the participants. And this is the sample of the certificate. The ID is there, and your full name will also be there. So on the last day, you can visit the website and just import the certificate ID, or you can type in your last name and you should be able to download the PDF version of the certificate. If you also want us to share that with you through any of your social media handles, we can also do that. But initially, we have everything on the website so that we don't have to do these things manually. And thanks ever so much to all of the volunteers for this year edition of the program and to all of our speakers that we have had so far. Tomorrow also, we'll be having 2 other speakers. And then the day after, we also have 2 other speakers. So we are probably here from some of our volunteers to welcome us on different days. And they are all here on the platform, and you can always chat with them and get more information from them. Please also, we encourage you to visit the various platforms that we have. That is the website, and learn more about the program. Also, our Instagram page and the WhatsApp group. If you are not there, we usually share the attendance record every day. So for you to know that you are capturing the attendance for that day, you can visit the WhatsApp group and also share it there. If you are in China, or probably if you have WeChat, then you can scan the QR code, the first one, and then I'm going to add you to the group because the group already have more than 200 persons. So the regulation for the WeChat group, if it's 200 persons, then you have to join by invitation. You cannot join automatically. You can also find us on YouTube and also on Facebook with the various names that are here on this picture. So just take a screenshot of it, and later on you can follow through. And at the end of the sessions today, we will do our selfie attendance to end the day. So please just stay until the very end. Stay until the very end because the attendance is not just taken at the beginning of the program. So probably if you just join and then you leave, you will not be capturing the attendance for that day. And as a fill over or a backup, you can always go to YouTube and then watch the video or just skip the video to the end where we took the attendance, and you can also check in case you are not captured in the PDF that we'll share at the end of the day. So thank you all for joining and continuing to drop your location in the chat session. At about this time, we are going to turn over to our speaker for today, that Tianyi Pan. And before he speaks, we want to say thank you so much for honoring our invitation to be here with us. We highly appreciate your contribution, not just to people in your own space, but people from different areas. It's highly appreciated. And the first time you were here, the participant really loved your presentation, and we were wishing to have you on the last edition, but it was not possible. So we are excited to have you here again today with us. We'll be looking forward to a very wonderful session. And also, let's give it up for our speaker. Let's welcome him officially to the platform. You can leave your, as always, just leave your message in the chat session to welcome our speaker. And Tianyi, it's up to you. You can take it up from here.
Okay.
Sorry, please. Good morning. The sound is extremely low for my end.
Yes,
That was
You're
all I
coming
know.
very
But
low.
what
I
about
don't know whether it's.
Hassan, please use the comment section. Oh, okay.
yeah. Is my sound coming okay? Because I think that was just Olano.
Yes, it's okay.
Yeah, my sound is okay. Yeah, thank you very much. Yeah, as you said, I skipped 1 year. I was here in 2023 edition. I like that very much. Unfortunately, couldn't do it last year, but here I am back, and I'm just doing something with my screen because I have 3 screens, so I want to make sure I'm sharing the right screen. So, just a second. Well, I'll try to figure this out. I had it already once, but didn't work. Okay, now it's working. So
Next, I'm gonna share my screen to you guys. Let's see, screen one. Yeah, should be the one. Okay, let me know if you are seeing this
Yes, we can see.
presentation. Great. So yeah, starting from the first slide, actually. Yeah, again, thank you very much, Olano, for the opportunity to speak again at OSCC. That last time was winter, now it's summer. And thank you all for coming, regardless of wherever part of the world you are at now. It's evening for me here. It's 7 o'clock evening in China. And I hope to give you a nice session. Last time I spoke about large language models more. And today, this year, it's going to be more basic stuff about machine learning and AI models in general. But as always, as Orlando said in the beginning, showed that you guys come from all over the different fields. So I don't want to speak so deeply. This is going to be a more like a very surface touch on what machine learning actually is and AI models. So not to confuse you guys too much, but if you're interested in this, of course, there's a lot of information and knowledge on the internet and elsewhere for you to go and dig deeper on. So today, what I'm going to talk about, I'll first, just like last time, I'll start to say something, maybe 10, 15 minutes about myself, just a short introduction, how I got into AI, because this is something that I'm not actually in, like started off as a computer science person, just like many others. So I came in actually from another field. Then we're gonna go into the actual meat of the today's agenda, which is machine learning and AI models. And as like just like last time, I'll end up with some of my thoughts about how you guys should approach this kind of learning stuff and such. But so let's start with why I am here and how I actually sort of ended up here. And the picture I want to start with is this. It's a Soviet era satellite. Actually, it's the first ever man-made satellite that went into space called Sputnik 1. And that was part of the Soviet and American space race when where these two big nations were competing to basically conquer space, send satellites, go to the moon. It all sort of stopped when the US landed on the moon and won. But actually, before that, before the US got the upper hand, the Russians, the Soviets, were able to send the first man-made satellite, this Sputnik 1 satellite, into space. And there's this Chinese or, well, Taiwanese guy from Google and other companies' fame called Kai-Fu Lee, or in Chinese, he's Li Kai-Fu. And there was a part in his book called AI Superpowers, where he talked about this AI's Sputnik moment, especially for China. And that Sputnik moment was back in 2017 when AlphaGo, the AI from DeepMind, now Google DeepMind, was playing the Chinese Go board game and won not only the Korean player Lee Sedol, but also the Chinese grandmaster called Ke Jie, both in 2017. Actually, the Chinese one was 2017, and then the Korean one was 1 year earlier, 2016. And the 2016 was also my personal Sputnik moment when I saw that match against Lee Sedol, the Korean grandmaster. I thought, wow, this is here's a picture of the Lee Sedol match. So I thought this is a technology that will change the world, basically. Because not only is it able to play games, but in the future, there's going to be all kinds of applications built around it. And because, of course, personally, I am a science fiction fan. And in the science fiction, in sci-fi, there's also a notion of AI in pretty much many of the stories. So that's also like from this imagination perspective, it also captured my attention. So this is how basically everything started for me. And what I do now, I do AI engineering at FuseFlow, a company called FuseFlow or a startup. And the product name is called Lipility. 2 years ago, wasn't this? I was in a different company called Clubotics. I'm gonna also talk about that a little bit. And still, I also still do side hustles, just like last time, with my own. I don't know if this is a brand or something. It's called Xiao Pan, because my surname is Pan. So in Chinese, Xiao means small, so it's like a little pan. And I basically built all kinds of AI applications. So so yeah. But my background actually, I was born here in China, but when I was really young, like 6 years old, I our family moved to Finland, so I grew up there all the way till I graduated from university. And I actually didn't study computer science or any technical thing. I was studying marketing at a business school. So I was a business graduate. I moved back to China. I still worked. Well, let's see some pictures. So this is the Fuse Flow or Lipility team that I work at now, and that this one is from my former one from 2 years ago. I was still in Robotics, and before that, yeah, when I was graduated from Finland, I actually worked uh, 5 years in this Angry Birds company called Rovio. Some of you might have still remember this game. Maybe you played as a kid on a mobile phone, where you pull the bird against the slingshot and try to hit some pigs. Um, and before that, yes, I grew up in Finland where the military conscription is mandatory. Um, and yeah, as I said, I grew up as a business student, so and my hobby was filmmaking. So really, it's about how I sort of became from this film person into this AI person. Well, this in this picture, I'm talking about AI, much like I'm talking to you guys now. So I'm making some speeches or lectures about machine learning and how to learn it. And this picture actually is me speaking about AI already in back in 2017. So 1 year after I got into this AI actually. And that was in Shenzhen, also China. Um, and how I did it, yeah. So you might be, especially those of you who are not from the software background or engineering background. How do you become this kind of AI person from a totally different field? First, what I did is I took some online courses. This is one of the first ones I did. This is a very old one. Nowadays, there are many more and I think better courses, but this one was what was available back in 2017 on a platform called Coursera. And this very famous AI person called Andrew Ng taught the lesson actually. So I don't know if you guys can see my mouse cursor here, but um, yeah, Andrew Ng, who was at Baidu and Google and at Stanford University, basically he founded this Coursera platform and put this machine learning course. And it was a really good course, but the problem is um, the language it used it wasn't the modern one. So they used something called MATLAB and Octave. Some of you might have seen that language from school, where you do some kind of basic math stuff. But in the real world, most of the people who do machine learning and AI use a language called Python. So I had to take another course in a different platform called Udacity. But the good thing is this course is free, or was at the time I took it. I think there is still a free introduction to Python course on Udacity. You can look it up. And one of the cool things about this course is, at least when I did it, it ended with a big project, course project that built a web crawler. And web crawler is this kind of thing that can visit websites and take all the contents from there and do something with it. So what did I do with the web crawler? I built this kind of box office predictor because I made films. I was my hobby was filmmaking, so I was very interested in films, and because I was learning about AI and data science and machine learning, I wanted to build something that had this kind of AI prediction, but in a world where I was familiar with, which was films. So basically, I set there used to be a website called boxofficemojo.com. Nowadays, it has been acquired by Amazon, so they kind of changed the website, and now you cannot use a web scroller to read the data anymore. But back in the time I was doing this, the website was still open. I could visit the website and basically read all the data they had about all the films that was released ever. So I collected a database of maybe 5,000 films, and was able to use that data to train a very simple model to predict the um, opening weekend revenue. So basically, whenever a new movie comes, I would take that new movie's info, who was the director, what kind of actors are there, what is the genre of the film? Is it like a comedy or is it a horror or something? And how many film theaters it's playing in the first weekend. So based on all this information, it will generate a prediction of how many millions of dollars it will make on the first weekend. And I even made it into this kind of Twitter chatbot or Twitter bot. Every week it will predict the new movies, and actually after the weekend, it will check what was the actual numbers. You can see sometimes it's very close. For example, this Zombieland 2 was predicted to be 27 million. It was 26.8. Here, maybe a more miss, 24 million, 37 million. But you can have sometimes good results, sometimes bad results. But that's the case of predictions. And my next project was this kind of very visual thing. Those of you who are in China maybe remember, if you ever saw on WeChat, this kind of mini game where you need to jump from a box to box. And at that time, I was luckily just learning about how to do computer vision. Basically means how to use AI to read the screen and understand what's happening in the screen or in an image. So doing all kinds of image-based recognition and prediction. And I was also learning about how to use GPUs. GPUs are these graphic cards that was first used for gaming, and now they are used to accelerate the AI learning. So I was also learning about the GPUs and how to use them to train models faster. And yeah, so how did I do this game? Because um, I tried to play it first myself manually using the phone, but I was really bad at the game. I would die after, like, my best score was maybe 77, right? And I was seeing on the leaderboard that all my friends have like 200 points, 300 points, 500 points. I was like, oh, everybody's going like past me. And then I was like, hey, but I'm learning about AI. maybe I could do something that helps me play this game by predicting where I need to jump next. But then I had some problems. I went to this very random WeChat group chat called AI Discussion, asked a bunch of like very technical questions, and there was actually some people who responded and helped me with the problem. And eventually I got it to work, and I put it to play the game overnight, right? I went to sleep. The next morning I wake up, I see that it has already got over 200,000 points. So at that point, I just made basically it didn't die anymore. So at that point, I made the bot sort of die. I forced it to die, and I saved the score. And that was a really cool thing. But how I went back to this chat group, and I told the guy who helped me that, hey, like a few weeks ago, you helped me with this project, and now I actually have made it work, and this is this high score I got. And it turns out this guy who helped me was the CEO of a company called Clobotics, so my previous employer. And they were doing machine learning and computer vision applications in these two uh, industries. One is wind industry, where they use drones to inspect wind turbines for damages and defects. And another industry where they take pictures of you know, the coolers and the shelves in the stores and identify the products in the shelves to provide data to the brand owners, like Coca-Cola, for example. So these are all like real world applications of computer science, computer vision, something that I did as a game. But now this was real, and the CEO actually offered me a job at the company. So it was really cool. And I ended up being there for 5 years until 1 year ago, I actually quit and joined this another startup. And here we do AI applications for more like uh, office workers, this kind of knowledge workers, AI agents. So this is maybe much more abstract. But yeah, just bear with me when I say it's a sort of knowledge workers or a kind of co-pilot for your office work. So when you try to write something on Word or Excel or whatever, this will help you. And I do this actually for part-time only because I also do a lot of freelance projects. That was actually one of the topics Olano wanted me to speak about last year, but I was too busy and couldn't make it. But yeah, just a few words that now that I do freelance, I can sort of um, plan my time better, or I don't have to worry about working full time. I can take a vacation whenever I want, and it's very flexible. And I kind of like this way of working. So apart from this part-time job, I also work for some of my own clients with sort of side projects that I spoke earlier. But this all like enough for myself, just to explain why how I came like from a totally outside the AI and machine learning world, and now I've been doing this for the past 7 or 8 years, and I'm already running like freelance projects and stuff like that. So this is the background of myself. And now to go back to the topic of the day, which is machine learning and AI models. So deconstructing this title, I wanted to speak, sort of take these two apart and address them one at a time. So let's start with machine learning, and then we'll move on to AI models just a little bit later. First of all, we have to define these words. And I've most of these slides basically these are not my pictures. I just found someone who made really good explanation, and I just took them. So let's start with the biggest idea, which is what is artificial intelligence. It's very abstract. It doesn't really say much. It's basically as it says here. I think it's well said that it's intelligent machines that mimic human intelligence. This is very sort of high level. It doesn't say how and what, just a general idea, right? And then machine learning is more specific because machine learning here it says algorithms enabling computers to learn from data. And I will come back into this, what it means to learn from data. But just now, remember this kind of idea that it's not something that we need to teach in advance. You can just show a bunch of data and you will learn. And then if you go deeper into this, so under machine learning, there is a subset of techniques called neural nets. And this is modeled more from biology. So human and other animal brains, they work like neural networks because there are neurons in our brains which are connected. I will also talk about this a little bit more later in this talk. So we build these neural networks in computers to sort of simulate what happens in our brains. And it turns out this is a very powerful way to do machine learning. But I'm going to start with some simple things and then we move on to the deepest one. And this deepest one called deep learning is just a kind of neural networks. Actually, nowadays, most of the AI you see out there is all based on deep learning. And deep learning is more like a brand word. It's more like a marketing word. What it really means, it's just a very deep multi-layer neural networks. So you just stack neural networks or neurons a lot on top of each other. And basically the sizes of these neural networks has grown exponentially these last few years. I'm also going to talk about this evolution later on, how the neural networks have evolved. So next, let's go back to the definition of machine learning and see how is machine learning different from the traditional software development that happens when we write code, right? So in traditional software development, if I'm a developer, I will write my code. I will tell the program how it's supposed to run. And if there's any bugs, it's because I made a mistake. I wrote something wrong and the program didn't run as I wanted. It's very logic focused, right? So I need to write everything. If my logic is not correct, then there will be bugs. So this kind of code writing on traditional software development is really good when the logic is very clear. I call it like if this then that. You tell the machines all kinds of conditions and basically give it a lot of rules for it to follow. But this kind of approach is not very good when the lines are so-called blurry or fuzzy, as they say. So one example is when you are trying to, let's say, identify different animals, cats and dogs. This is a very traditional example. On the one side, there are cats. On one side, there are dogs. If you show a picture, how do you know if it's a cat or a dog? Sometimes there are cats that look like dogs. Sometimes there are dogs that maybe look like cats. So sometimes there are very fuzzy line in between these two kinds. And if you're just trying to write some rules how to identify what is a dog, what is a cat, it becomes really hard. We'll also see later on in this talk this specific example of cats and dogs. If you try to approach it with a rule-based kind of approach, you will see that there will be some challenges. But it might be easier if you have a lot of pictures of cats and dogs and you can just show the AI and let it learn itself. Okay, this is traditional. And if you go to machine learning side of things, here, just like we said in the beginning, the programs will learn itself from the samples, from the data that you give it. So we give it tons of pictures of cats, tons of pictures of dogs. We don't need to tell it what a cat looks like or what are the rules that define a cat. The neural network or some other way to process the picture will learn that definition or distinction itself. So it's very data focused. It's very experience focused. You have to sort of show the AI and not just tell the rules. And it's sort of the opposite of traditional software development, where when the problem is very hard to describe in just words, then this approach is very good. And it's not so good actually, or let's say it's less good than traditional software development. If the rules are very clear, you can still show a lot of samples and let machine learning algorithms to learn these rules. But then again, if the rules are very simple, it's actually easier to use the traditional software development and program there. So machine learning is also not always the best solution. If the problem is very simple and you can solve it using traditional software development, then you should do it with traditional software development. But if it's this other kind of problem which is fuzzy and difficult to describe, then machine learning actually is better. Another way to describe this difference is if you think about how people learn. And this traditional side is maybe how you learn at school, where the teacher, or in the software development case, it's the developer who writes code and tell you all the rules, and you have to follow these rules. So you learn this at school. But then from experience is how you learn as a small kid, where you just do random things in the world and see what happens. And probably all of you now, when you see this picture on the right, you will guess what will happen to the toy in the hands of this child. But the child has to try it many times before they learn that the world has gravity and things fall down. Okay. So that's the difference in my mind about traditional software and machine learning. Let's talk about these models, machine learning models now, or AI models. And I'm going to start with the example of what I think is the simplest one, called linear regression. And it falls under this supervised learning um, type. So basically, in supervised learning, you are supposed to give the so-called right answers to the AI, and based on the right answers, the AI will adjust and becomes better at predicting. So you probably have all used supervised learning in that way if you ever used linear regression. And even if you don't know what linear regression is, you still probably have used it. This is a very simple example. Anyone who has maybe played around with Excel, Microsoft Excel, the spreadsheets, you have done something like this where maybe you do an experiment and you log all the data, for example, the temperature of different days and how much ice cream was sold in different days. And when you plot this data on this 2D chart, for example, where the x-axis is the temperature of the day, and y-axis is how many ice cream was sold, you maybe get this kind of rough line. And when you ask Excel to solve you a linear a line, basically to cross between all these points, it is doing just that. It's doing a simple machine learning model called linear regression, and it will not generate, but it will fit a line. And the way this fitting works is that on average, this line sits right at the middle. So although each point is maybe a little bit ways off, from this line, but on average, all the points are as close to the line as possible. So this line is the best representation of all these experimental points that we have collected. And if you think what this line tells you, actually, this line will tell you, given that you know how many degrees it's outside today, maybe it's 20 degrees, how many ice creams can you expect to sell today? So basically, it's trying to predict along this line, based on the temperature, how many ice cream you should prepare for today, because you're going to sell 175 ice cream if it's 17 and 5 degrees outside. Basically, this is what the model tells us. It might be off a little bit, but it's a good prediction because we can see that actually all the points that we collected from the real world falls along quite nicely along this line. But does it work always? It's the question, right? There are sometimes limitations. For example, if you try to extend the line down all the way to 0 degrees, well, this will say something. Actually, we can see here from the y-intercept. It will say that even when the temperature is 0, you are expected to still sell 14 ice creams. But we probably know nobody buys ice cream when it's winter and it's cold. So maybe this model doesn't work when there's no data, because we haven't collected data from here. We actually don't know if this prediction, if this model is valid. So this is something we also need to consider when we build models, so that maybe they don't work where we don't have the training examples or the right answers to give it to train. So we cannot expect the model to be universal in a way, although here it looks like it's a pretty perfect line. And remember when I talk about the box office bot, actually it's just the same as the ice cream thing. It's actually just many linear models sort of put on top of each other, stacked on top of each other to arrive at the final prediction number, how many $1 million, right? So maybe the temperature, if we just forget about the movie example and still think about the ice cream. So we already see that there's a linear relationship between temperature and how many ice creams you sell. But maybe there are other things that also affect. Temperature is something that varies sort of in a smooth fashion. So you can have any value between 0 and or even under 0, less than 0 and 100 degrees or whatever. But then rain or not, it's more like a binary. It either rains or it doesn't rain. But you can still use a linear model to basically predict what happens if there's a rain. Well, my hypothesis is you will sell fewer ice creams, right? And workday versus weekend. Maybe on the workday, everybody's at work or at school. You don't have so many people outside to enjoy the sun or whatever. So you sell less, but weekends you sell more because there are more people. And there might be other things to consider. Are there any events happening nearby that maybe if there's a concert, it will bring more people and then you will sell more, right? Is there anything else you can think of? You can just like imagine all kinds of different things that affect the sales of ice cream that you can test, if you know the right answer. And this is what we call feature engineering. And coming back to the cat and the dog example, before we had neural networks, maybe we as a humans will think about different things. For example, how to define rules that say what is a cat, what is a dog. Maybe you look at the shape of the ear. Maybe you look at the shape of the face. Maybe you look at whether the animal has whiskers or not. So sometimes these are actually all binary. So it's either one or the other. yes or no, yes or no. And then it will define if it's a cat or it's not a cat, which means it's a dog. So this is a kind of technique called feature engineering, where we as a humans try to think about different ways to give rules, and basically if you follow these rules, this is called a decision tree. So if you follow these rules and look at the ear shape, okay, if it's pointy, go to here, and look at the face. If it's round, then it's probably a cat. If it's not round, probably not a cat. And you also look at this side. If it goes here and has floppy ears but whiskers, it's still a cat. But floppy ears and not whiskers, it's probably a dog. So you kind of follow this logic. But the problem in this sense is you have to tell and think about these features in advance. And sometimes you just don't know it. Sometimes you cannot explain. And it is these ways where neural networks really was shining. So it's really like doing its good. And how the neural networks came to be, well, again, we tried to follow something from biology. We tried to mimic this biological cell, the brain cell in our brains that we call the neurons. And how it works is it takes some inputs on one end, and then it processes this data, and then it sort of gives outputs, which means it will pass this information along to the next cell and to the next cell and to the next cell. But sometimes it doesn't pass along all the information. So if some information comes in, maybe only half of the information comes out. Maybe it doesn't pass any information out. So whatever happens inside this one cell is decided by the logic inside. And if we try to use computers to mimic, to simulate the brain cell, it's something like this where we have some signals coming in as inputs into this neuron. And inside the neuron, there's some very simple function that says when you count all the input signals together, when you sum it up, some value will come out from the other end. Sometimes it doesn't output any value. It depends on the sort of internal multipliers, what we call weights. So some number here will weight against all the inputs, and it will become an output. And one neuron is as simple as that. It's just adding things up that comes in, and you multiply it with some weight, and then out comes some output. But somehow when you put this single neuron into a network of many neurons, you start getting really magical results. And here I'm just taking a second to jump out and show a little bit of this evolution of how neural networks and this research has worked. And here I'm talking about the artificial neural networks, right? So this is not biology, or this is not medical research. This is not neuroscience. It's not looking at how human brains work or animal brains. It's only looking at how this kind of digital neuron simulations could simulate brain activity. And actually, if you see this face and this name here, called Geoffrey Hinton, and he is I'll show later, but he was really like foundational in this neural network research, because he and his colleagues, teams, discovered this technique called backpropagation, which allowed the neural networks to actually learn from data. So I already showed you with the linear regression, with the Excel sample, how the machine will fit that line across all the sample data that you collected. But actually, for a long time, people didn't know how to do it for the neural networks, how to get that information back from the training. But these guys figured out technique called backpropagation, which allowed you to sort of send this correct signal, or like you can tell the model that it was correct or it was wrong, and then the neural network will adjust itself. So this is how deep neural networks work. It's not really deep because it only has like 5 layers. And on the very outside, there's this input layer which looks at things, right? You can give it a picture, you can give it data, you can give it whatever. And these neurons basically just turn this raw input data, they capture it and send it forward. And let's skip the hidden layers first and look at output. So on the output side, maybe you have different layers that will tell you how strongly this model thinks. In this case, it's a classification problem, right? So you are trying to identify the the species of the picture here, of the animal. And after all the processing, this middle neuron will have the highest output. So this number is maybe 0.8 or 0.9, while these other two are close to 0, which means the neural network thinks that should be this middle answer, which is the bird. It's never like 100% sure. So there's always a little chance that it might be some other thing. But usually when the model has been trained well, it has understood the picture and it can tell it's a bird. Okay. So what happens in these middle layers? Middle layers is where the information actually it gets processed. So, and this is something that sometimes we call black box because we cannot explain it fully. But through training with the training data that will tell the bot, tell the AI whether this picture is a bird or a dog or a cat, the model learns to adjust these weights, like I said, these multipliers in each of the neuron. So every time a new picture comes in, these neurons in the middle, they fire differently and they pass the information differently so that when it knows it should be a bird, in the end, when you multiply all the values up through the network, the middle neuron in the last layer will be highest, and all the others will become lower. This is how you train the model. So you sort of tweak these weights in the middle little by little until it works with the training data so that a bird picture will become a bird signal in the end, and the picture of the dog will activate this dog signal, and then the bird signal will go down. So this is how the neural networks works on a very high level, right? I'm not gonna go too deep in. There's a lot of math involved, but probably if you are not doing computer science, you're just trying to understand this, it's enough for you to know that this is how these artificial neural networks will simulate how human brains work. And let's look at how actually if you go back one slide, we can see that already in the 80s, right? It's almost 50 years ago. They sort of figure out a way to train these neural networks. But actually they had to wait 30 years until 2010s before we had good enough computers to do this. Because as I said, there's a lot of math involved, a lot of computations, and there just wasn't enough computer power to do this kind of computation until something called GPUs was invented. And I don't know about you guys. Probably, if you're still students, you're pretty young. But when I was growing up, when I was a kid, back in the 90s, right? I grew up in the 90s, and I remember then there were these what we still called 3D cards back then. They're called 3D cards, these 3D graphics, because they are used to draw the 3D worlds of the games. And that's when the first GPUs came. They basically accelerated the way you can draw the 3D worlds of the games. So the first use case of these GPUs was gaming. I bought a lot of GPUs just to play a lot of games. But everything changed when NVIDIA, and I'm not a part of NVIDIA, but and this is not a paid advertisement, but NVIDIA really did good on the GPU when they added something called CUDA in their 3D cards, which allowed researchers basically to not just program the cards for games, but for other kind of computation. And it just happens that the way these GPUs are made or designed, that they are really good and really fast at solving the problems of like calculating the values of neural networks here. So in a sense, GPUs was very good tool to make computations here in the neural networks much faster. So when the technology, the CUDA technology evolved, and back in 20, uh, not in 2012, I think it was 2016, when the first image recognition models came that you can train with GPUs, and these are really good ones who got a very high score in different kinds of benchmarks. And as you say, the rest is history. So GPUs was a really sort of pivotal moment, and we can see here in the next slide how different NVIDIA chips, how powerful they got. So back in 2012, and I started off around this time, 2016, 17, and there was already GPUs, NVIDIA GPUs like V100 or 800, and nowadays there's H100 and H200 and more. So you can see that the computing power just grew exponentially. And not just computing power that grew, because the more compute you have, the bigger models you can train and use. So if you have more powerful chips, it's only natural that um, the model size also become big. And here we can see that this is back to the language models that I spoke about actually 2 years ago. And this is actually one of the same slides I used back then. But I'm just trying to show that how the sizes of the models grew as time went on, just like the power of the GPUs we had. So it grew in line with that kind of number of power or amount of power we can get. And that like in 5 years only, like last five, not even last 5 years, but from 19 to 22 was 15,000x increase in the size of the language models. And just like look at how old this first model is, from 2017, called Transformers. And this is actually the language model that Google, the researchers at Google invented. And they use this AI architecture, or the way to form this neural networks to train these language models in a self-supervised way. So as I said earlier, the sort of supervised learning is when you tell the AI the right answers. If it's a cat or a dog, and it will learn from this right answer to adjust the neural network. Well, self-supervised is this special case in language models where it's easy to do because you can just copy paste a long bunch of text to the model. And because you have the long text, and every time you start the sentence, let's say, the animal didn't cross the street because it was too tired. You can train it by showing first the one word, the, and then it you can tell the right answer to predict the next word, which is the animal. And then you show the animal, and it and so on and so on. So it's almost like why it's called self-supervised, because as long as you give it a bunch of text, it can train itself just trying to write that text again. So then it will know the probability of how the next words will come out based on the previous words. You also have this technology not only in chatbots, but remember when you are trying to type on your phone and you write some words before and it can guess the next word. So basically it's the same kind of technology. So I'm only showed you a couple of technologies here, like the image recognition, language models. A lot of other applications have been built on the deep learning technique, basically the neural networks. So yeah, I saw the first two, language processing and image recognition. You can do stock predictions. You can do drug discovery, healthcare. I have an example later on about this. You can do speech recognition. You already have all this like in Amazon and in Apple's Siri and other things. You have self-driving cars, all kinds of things here. Many of these are based on neural networks because it has turned out to be such a powerful way for machines to learn. Basically, it's such a powerful learning algorithm. Okay, let's talk about the results from last year's Nobel Prize, which was a surprise even to myself. Remember Geoffrey Hinton we talked about earlier? So he was one of the two people awarded Nobel Prize in physics um, for foundational discoveries and inventions that enable machine learning with artificial neural networks. So you remember he was the guy who was part of the team that they invented how to train neural networks, even when they didn't have the proper GPU and compute to do that. So the neural networks were really small back then, and it was really slow. And actually, nobody believed that neural networks was the way. Everybody thinks, yeah, you have to write a lot of rules. You have to go to school, right? But Geoffrey Hinton and some others believe that you just need to show more data, and when you have more compute, more GPUs, and then the neural network will work itself out. And yeah, nobody believed him, but he was right in the end. And when we talk about the medical and biology applications, last year there was another winner in chemistry. These two guys, actually, Demis Hassabis and John Jumper. They are both from Alpha DeepMind. So remember in the beginning, I told that my interest in AI started when AlphaGo was playing the Go game. Well, it turns out these guys went much further than just a game. They developed an AI that can predict how proteins fold in this kind of 3D space. And this is very important in medical research because there are millions of proteins out there in the world, and the humans know very little about them, how they fold. But if we know how they fold in this kind of 3D structures, um, this will help do a lot of drug discovery and other research. So just to give you a sense of how big the DeepMind contribution was to the world, uh, before 2023, so before two years ago, the whole of humankind only were able to know about 200,000 proteins, how they are folded in real world. 200,000, okay? And you can do it with very slow process called X-ray crystallography. So it's a very slow and expensive scientific process to figure out the 3D structure of these proteins. And for some proteins, it doesn't even work. But when DeepMind released their latest AlphaFold 2 AI, and they won a competition that was trying to predict the 3D structures of proteins. Before they released AlphaFold 2, I think the best predictions were about 60 points or something, 50 points, 60 points. And then with this new AI, they were able to get to over 90 points. And that's when they knew that this was good enough for actual use. So what Google did, or DeepMind did, was they used this AlphaFold 2 AI to predict all 200 million protein structures. 200 million. So before that, we have only tested 200,000. From 1,000 to million, that's a 1,000-fold increase. So basically, DeepMind has gifted humankind thousands folds of information that we didn't have. Of course, these predictions are not perfect. There are still mistakes, but they should still be good enough for a lot of different scientific research. And you know what? They released everything for free. So they basically open source it for people to use. And that's a big contribution they did. So I think them winning Nobel Prize is warranted. But so this is the sort of end of my official sharing part. But I just want to give a few takeaways. These takeaways are similar to mine 2 years ago. But looking at this story of DeepMind and especially the DeepMind CEO and founder, Demis Hassabis, I think that story is very inspiring because, I'll show these takeaways first. But I'll tell you the story of Demis Hassabis if some of you didn't know yet. So Demis started off as a chess player. That's why he liked Go and chess, this kind of tabletop games so much. And he was like a small kid. He was like a genius kid who played chess. And then he went on to make computer games. He was in a UK studio called I think it was called Lionhead. When I was a kid, I knew that studio. That there was a legendary CEO of that company, and called Peter Molyneux. And Demis Hassabis worked for him, like this legend in the games industry. But then he wanted to do AI. He wanted to study, and he actually quit the Lionhead games. And he went to Cambridge. Went to Cambridge and study AI. And then he founded DeepMind. He did AlphaGo. He did AlphaFold. He's trying to do AGI, which is artificial general intelligence. That's probably something that we don't have time to talk about today, but it's also a very interesting, like, can we actually build AI that is at the same level of smart than humans or even smarter? But that's maybe something I will lead to the future. So yeah, thank you very much, guys. Yeah, to say a little bit about this takeaway. So when you think back about your life, what direction you want to go, I think it doesn't matter if you're not a computer science guy, you're not an AI person, or you're not even engineering student. I don't think the background matter. My background was also like really random. I was filmmaker. I studied marketing. Now I'm an AI guy. So I think more matters is where you're headed, where you want to go, not where you're at now. And about learning, yeah, I think curiosity trumps everything. So, like I did with the jumping game, you can start with or the box office predictor. You start off with the problems you see around you in the real life, because this give you motivation. You want to solve these simple problems, even if it's very simple, like beating a game, because you don't like that your friends are ahead of you. You want to beat your friends. These are very petty and vain motivation, but they're motivation. They keep you going and sharing. Like this session, like I did the talks before. I like to write articles about the projects I build. So why I want to do this is because sometimes when I was doing it, I was hoping maybe there was someone else who did it before me, and they would leave these kind of journals for me to read and learn, so that I don't need to go around so much. And sharing also helps you connect with other people. So in the end, they might also give you more opportunities. Like after I was in Clobotics, I was doing a podcast about AI, and we would interview a lot of people. And one of the people we interviewed in the program was actually the founder of FuseFlow, this Lipility product company. And she just came to my show to talk about her company, and we became friends. And later on, I joined her company. So you kind of also network with people when you share and when you learn. And mistakes are also it's a part of the journey. Actually, mistakes are the biggest helpers because you learn from them best. You learn to embrace mistakes because you learn from mistakes. If everything is just so smooth with you, you actually don't learn anything. It's too easy, right? That's where true growth happens. And if you make too many mistakes, maybe it's because the direction is not correct. So then you need to do some course adjustments. But I think overall, if you have like a long-term goal, yeah, I need to learn about AI. Yeah, just start using AI today. Go into the world. There's a lot of free resources, YouTube, blogs, this kind of yeah, OSCC, OWCC, these kind of events really help you learn a lot of things. Just be curious always. So yeah, that's all my takeaways for you guys. Thank you very much.
All right, all right. Thank you so much, Tianyi. Thank you so much. I'm sure probably if you were following the comment session, there are a couple of
I didn't actually. I see a lot of chats going on, but I'm
yeah.
sorry, I had a full screen on, so I didn't see the comments
Oh,
now.
okay. But I'll also try to share with you.
It's in highlights, yeah.
Yeah, I'll also try to share with you. We will be having the second speaker, Hellen Momoh, who's basically going to talk about the mathematics behind what you have just talked about.
Oh,
So
great.
maybe if you can hop around a little bit, then we can probably have a discussion, probably maybe at the end of our training. But if you have something to do, then I will also update you. But thank you so much for sharing, and that was really interesting. And I'm sure everyone actually loved
There's a question in the chat box.
Question in the chat box. Okay, I'm coming. We just take, if there are questions, I will take two.
Okay. Yeah, please help me route because I didn't read through during my presentation. Sorry.
Yeah, I think I even muted myself as well. Helen, you can also unmute yourself. So let me take this question from the chat, and there we take Lomo, who hand is up. Yeah.
I actually see one question there because there are a lot of comments are about thank you. So one question was from Collins.
Yeah, I think that's the question.
Okay, so let me read.
From Collins. Yeah.
On what basis or criteria do you choose the value of bias and weight in the neural network or for chosen project in order to achieve? Bias and weight are the things that the neural networks will learn itself. So you don't need to choose the values. Usually what you do is you initialize the neural network with some random values so that it doesn't go always the same way when you train it. But as you show the training examples, it will automatically, through the backpropagation that Geoffrey Hinton and others discovered, through the magic of backpropagation, the network will automatically adjust itself, the biases and weights. So you don't need to choose the value per se, but through the training, you will end up with what probably is going to be the best values.
All right. So let's take Flomo as the last person
Thank you very much,
because
sir.
of time. Flomo, you can unmute yourself and ask your question. Flomo.
Yeah, thank you to the presenter. Yeah, the presentation was very splendid. But there's one question I have because I've also though I'm from I'm a bioengineer, I'm a student of bioengineer, uh, and I'm actually with nanotechnology because
Okay.
I've been synthesizing a lot of nano enzymes to detect and treat pathogenic bacteria, with most
Oh.
applications in food safety. But
Okay.
yeah, of one of our recent papers, yeah, we wanted to have this kind of synergy wherein we were integrating nanoenzymes with an AR model, okay, to improve how fast we could detect some of those food spoilages and improved their shelf life as well. But this was one of the problems we encountered, right? Some of those colorimetric inferences signals could not easily be, I don't want to say identified, but analyzed by the AR models we were using based on some natural effects. Like, because, for example, when you use the cell phone and then capture images, the model takes the model found it very difficult to analyze those images and then predict our result for us. Another was that based on some lighting effects, okay?
Yeah.
Some lighting problem, some lighting was also a problem. But then I just want to know how could we sometimes try to curtail some of these things? Because when we encounter some of these natural activities, it also affects our results as well.
Yeah, that's a very good question. I think if you want to be a very scientifically rigor, you cannot really use this kind of everyday environment to perform this kind of measurements, because, as you said, the quality of the camera, the lighting conditions around the environment will affect the way the camera sees the image. Of course, you can try some pre-processing to try to sort of normalize the data before you feed it into training or prediction. So that's what you can do, but you are still limited if your environment is out of control. So usually when you try to do this kind of scientifically rigorous experiments, you probably try to control the environment. So you're always doing kind of some kind of lab, and you have a camera, sort of static camera set up, and you put the food stuff in a well-lit container where you take photos. But these are all like perfect situations. And you can only, I think you can only sort of prove that under perfect conditions, maybe the model can identify something. Even that's not certain, right? It might be that you have the perfect conditions and still the camera doesn't capture enough. I'm not an expert in the field of sort of food waste and sort of food going bad, so I kind of imagine what it'll look like. Maybe just some mold or something like that. That's my very basic understanding of how food goes bad. But yeah, so you need to also, one thing about AI applications is machine learning is only one part. On the other part, you need to have experts in whatever it is, this like food chemistry or biology of how things go bad, and you need to understand that part also, so that you can design a proper experiment and proper way to train the model. So basically, you need to ask the right questions first before you can get the right answers. This is a very roundabout way to explain, but
Yeah,
yeah,
I think.
maybe you had some ideas.
All right. So thank you so much, Tianyi. That was great. And now we will be. Those that want probably PPT or contact with him, I'm going to reach out to him later on, and then we can
I
fix
can
that.
send. I'll send it to you. You can then share it.
Oh,
Yeah.
okay. Okay. Thank you.
Sure,
So
because some
let
of
us
us want to,
welcome.
some of us want him
Sorry
to be
because
our
of time.
mentor.
Collins.
So
Collins,
some
sorry
of us
because of time.
want him to be our mentor because the explanation was very clear, and we are on the right
Okay.
direction. Yeah.
Thank you.
All
Thank you.
right. He will. He will get back to you guys. So let's go quickly to our second speaker, Helen. So Tianyi, you can stop sharing. Okay, good. So Helen, you can take over. And as always, let us welcome our second speaker. Let us welcome our second speaker in the chat session. Let's welcome our second speaker. She's going to take us through with what she has for today. Okay, we can see the screen. You can put it in a full slide mode. Maybe, okay, you're using Windows, so maybe F5. Yeah, but you can try to also speak. Let's know we
Can
can
you
hear
hear
you.
me? Can you hear
Yes,
me?
yes.
Okay. Um,
Okay,
can I
you can go
start?
ahead, but I think the slide is still in the other mode. Probably you can put it in a presentation mode.
Okay, hold on. Okay, so there are going to be two slides, two PowerPoints. So if I do it manually, that's fine. Is it okay? Can you see it?
Yes, we can see it.
Okay. So thank you, Pan, for the wonderful presentation. It kind of made the job easier for me. It was really clear and it was very, very helpful. So guys, my name is Hellen Momoh. I am a data scientist and a machine learning engineer. I'm in my last year here at Harvard, doing my master's. So first, we will go through the maths behind AI, the general concept of math behind AI, and then we will talk about all the important maths in machine learning. So first, we start with why math in AI and machine learning. So someone will say math is like the engine that AI works on, right? So it's like the backbone of machine learning as well, where every algorithm, whether you are building a simple regression model, you are building a decision tree model, you are building a deep neural network model, all of these models and algorithms are powered by mathematical principles. So understanding the maths help us move from behind being just users of AI systems to creators and innovators. So, why math matters? Someone will ask. Interpretability. So, math allow us to understand what models are doing and why. And then fairness, like probabilities and statistics, on the other hand, allow us to understand and detect and reduce bias. And then innovation, new architectures and algorithms are born from mathematical insights. And then reliability, right? So math also help us build robust, trustworthy systems. So if we cannot understand, first of all, to do machine learning, data science, or AI, you have to have some level of basic understanding of mathematics. Because when you understand math, you are able to know what is happening at the background. So we'll go through some of the most important, just few of the most important maths in AI. Like we see here, we represent data as vectors and matrices, which leads us to linear algebra. We make decisions, optimization, and logic, which leads us to multivariate calculus, derivatives, and so forth. And then we learn patterns, which lead us to gradient descent and probabilities, and then enables interpretability. Now it's called explainable AI, ensure fairness and drives innovation. So linear algebra, for example. So linear algebra is the core language of AI because what we see as data are just bunch of matrices and vectors that we are representing. So for example, we have scalars which are like single values, and then vectors which are like feature sets, and then matrices which are our data sets, and tensors which are high dimensional data sets. So when you come to deep learning and you are dealing with tensors, you're trying to predict whether this thing is a cat or it's a dog and so forth. So the data set that we see in Excel that Tim was presenting, they are all just bunch of matrices. And that is how they are seen and absorbed by the computer. We call them data sets. The computer will call them matrices and vectors. So, and then the dot product also, which is very important in linear algebra, which help us capture similarity and usually using embeddings and attention. And then we have matrix multiplication, we drives like forward propagation. So when we go to deep learning, we're going to learn about forward propagation, which is how the model takes the data set and then start to train on it and make inputs. So, and then we have back propagation, we have gradient descent optimization, we have atoms and so forth. So, and then one way that is important to think of data is as a clay. And then the way to think of linear algebra um, is like the hand that shapes the clay into something more useful. So we talk about scalars, right? So there is something in machine learning called learning rate, for example. You can represent a scalar, a single number with like 0.1. So the learning rate is how fast you want your model to learn. Do you want your model to learn slow, or do you want the model to learn fast? So if you understand the concept, you actually, most times we are encouraged to choose optimum learning rates, because if your model is learning too slow, so if you set your learning rate to 0.1 and your model is learning too slow, it may take forever for your model to train, and it might be computationally expensive. But also, if you set your learning rate to, let's say, 0.9, the learning rate, the model will learn fast, and then it's going to miss all the corners that it should capture before making decision. So sometimes it's important to have a very balanced or well-balanced learning rate so that your model can learn well and not too slow and not too fast to miss the midpoints. So, but in machine learning, we call it learning rate. In algebra, we call it scalars or single values. And then we have vectors, right? So vectors are like other arrays, like feature vector, like the height, the weight, the age of this person, trying to put a group of people together, and so forth. So we will define these terms in machine learning, but in math, they are called vectors, and the machine treat them as vectors, not the way you and myself will call it. And then we got matrices like 2D arrays, three-dimensional arrays, n by n matrices. So this is like the data set. So most machine learning algorithms or models cannot be trained without data, right? Now we have LLMs, which are mostly pre-trained, but you still need some kind of data sets to adjust, these LLMs to your use case. So these matrices are our data sets. They are our Excel data sets. They are our unstructured data sets. They are our how is it called? Our natural language processing data sets. And then we have tensors. So we have AI, we have machine learning, and then we have deep learning. So in deep learning, okay, I would say deep learning is an advanced form of machine learning, and that's where we deal with tensors, and that's where we have high dimensional data sets, where you see tons and tons of images, and then you see different really advanced different things happening, like self-driving cars, like Siri, like Alexa, like Google Maps, and so forth. So those are all deep learning neural networks, and those are all deep learning algorithms. So the way in which to represent them is by having high dimensional data sets, which are called tensors in linear algebra. So But there are key operations in the entire thing. Number one is the dot product, where we measure similarity that is used mostly in attention mechanisms, and then matrix multiplication, which like powers neural networks layers. For example, in a neural network, we have an output. First, you have an input, and then you multiply it by the weights plus the biases, and then you have your outputs. So that's how important it is to understand the foundation of these models. So when I started, when I wanted to do my master's in data science, I was doing economics and computer science minor at Georgetown, and then I was like, oh, I was struggling because I did not understand the concepts of machine learning and the models I was building. The theory was there, but I didn't understand how these things were working behind the scenes. So I switched my major and did interdisciplinary mathematics for my first degree at Georgetown. So another important concept that I want us to look at is calculus and derivatives. So calculus is how machines learn from mistakes, and then derivatives measure change, and then gradients generalize to many variables, and the chain rule, which is backpropagation. So backpropagation in machine learning is how the model goes back to make correction after it has made an output or a prediction. So usually when we build machine learning models, especially with heavy kind of data sets, we kind of like experience error. We kind of see there is a huge error between what we are predicting and what is expected. And the thing is, when we build machine learning models, we expect our error rate to be lower. We expect our error rate to be small. So when you build these things and then you see your error rate is high, you cannot present it to your manager. No, you can. I mean, you have to find a way that you can work around what is happening in the model. So when you initiate your backpropagation algorithm, it goes back to make this correction for you gradually. So derivatives, like I said, the rate of change, and then creating a vector of partial derivatives, and then the chain rule, backpropagation, and so forth. So the way gradient descent is computed is like this. So you have your weights or your inputs, your old weights, you equals it to your new weights, and then you minus your learning rate, and then you multiply it by your derivative term. So all these things you have to understand how it's working, because sometimes we see these very beautiful models, but if you do not understand the math behind the hood, you get completely lost. So it's important to get the foundation. So, and mostly we do this to find the parameter L, which is the loss function, and the learning rate, which is an action that we send to our model to learn. And then probability and statistics, right? So AI must handle uncertainty, that's for sure. So probability in AI and machine learning quantifies uncertainty, while statistics help us make inference from data. So if there is no probability in statistics in AI and machine learning, our algorithms will be arrogant, and they will not learn uncertainty, and they will just keep going on and will give us false outputs all the time. So the concepts of probability deals with like random variables, distribution, binomial distribution, normal distribution, and then the Bayes theorem, which everybody know, the probability of A equals the probability of B over A multiplied by the probability of A divided by the probability of B, whatever. So these concepts guide uncertainty in machine learning prediction. So the Bayes theorem, we have the Bonferry theorem, and so forth. And then the concept of statistics is our mean, median, variance, mode, and then hypothesis testing, and then correlation versus causation. So most times we mix the two, right? If this event happened, did this even make it to happen, or was this the reason why this thing happened? And then hypothesis testing, you want to find what is true, what is not true, what can be proven, what cannot be proven, and then your mean, your median, your variance, and so forth. So when you understand what your mean is, what your mode is, what your variance is, and how far these numbers are from your data sets, you'll be able to model your machine learning algorithms properly. So usually what I do when I started, because right now it has gotten to a point where I get overwhelmed to like build the big stuff. But when I started my foundation in data science and I took a course I took a 6-month postgraduate program at MIT, what I would usually do, because it was a beginning, I would take the data set and I will like feature engineer the data set. So when I go through it, I understand what is the summary statistics of my data sets. So when I see the summary statistics of my data set, I'll be like, okay, so this is our mean, this is our mode, this is our variance, this is our standard deviation, for example. And then how are these numbers different from their others? And then I also go on to see if we have correlation heat maps to see how the data that I'm about to model, how they are intercorrelated with each other. So you will never really understand the results of your machine learning model if you do not feature engineer, if you do not visualize or run summary statistics of your data set. Mostly, I use Python for those kind of problems. And then the next one is your optimization and your loss function. So in machine learning, we have all these terms. So optimization is about finding the best parameters that minimizes our error. So this is framed like this is like the simple way to put it is like I have this problem and it's sitting right here and I need to minimize the error. I need to fix it. But for every time I go to fix it, the error just get bigger. The problem gets bigger. So that is when we introduce optimization in machine learning. So we have, for example, gradient descent optimization. We have Adam, we have RMS probe, we have stochastic gradient descent. In deep learning, the data sets can be so huge to the point where you have to introduce dropout method. So for me, what mostly work for me to reduce my error rate, I like to use dropout method. So when I use the dropout method, that means you split the data set into two. So you train 50, the data set learn on 50, and then you test, and then you test on 50, and then you go through it again. Some people like to use the 70-30 rule as well. So there are different optimization that help us reduce our loss function, because that's the essence of building all these big models, to reduce error, improve prediction, and so forth. So the way in which we measure error, there are a couple of ways that we can do that. So we have the mean square error. So the mean square error is used in regression problems. So where you are dealing with numbers, you are dealing with ages, you're dealing with prices of used cars in the market. You use the mean square error to see the difference between what you predicted and what was expected. And then we have categorical cross entropy that is used in classification problems. So classification problems are like predicting binary outputs like yes or no, cat and dog, and so forth. So you use categorical cross entropy to see to get your loss from your actual and your predicted. So like regression classification, linear regression, multiple linear regression, classification, and so forth are under supervised learning algorithms. And then we have other unsupervised learning methods like clustering, where it comes to disease prediction, or what makes up how are these things similar, and so forth. So there are a lot of building blocks in machine learning for beginners that you have to take your time to understand if you want to be a good data scientist or machine learning engineer. And then what is our next one? Okay, so we're talking about math in deep learning models. We'll go to that next one very quickly. So math in deep learning is like models that are stacked by many mathematical functions. So we have each component that deals with activations, convolution neural network, attention, and so forth. So the math in deep learning is where we mostly deal with all the different gradient problems, where we deal with activation functions. So activation function is like telling your model, activate. I've built you, but activate. But again, you can only choose your activation function if you based on the problem you're solving. So if I want an output, if I want my model to give me an output between 0 and 1, like tell me, hey, function, my mother is going to tell me, hey, Helen, this is one, this is a dog, or this is a cat. Or I would say, give me ReLU. So most of my professors like the ReLU activation function because they believe that ReLU is also takes negatives and takes 1, 0, and negative. So if you say, give me 1, if this is my if this is a dog, give me 0. If this is a cat, and give me -1 if this is something else. So it's really depends on the problem set and the problem you're trying to solve. And then we got convolutions, which are CNNs, the way Tesla work, the way self-driving car works, the way objects are detected, where we have different pixels, where we have these algorithms extracting features and so forth. So most times in CNN, we use the softmax activation function. So it really depends on the kind of problem that you're trying to solve. And then math in real world, right? So math allow everyone who's into AI or AI practitioners to move beyond black box systems. So it enables fairness, it enables robustness, explainability, and so forth. So one of my favorite tools now in machine learning is explainable AI. I want to know why my model is making certain decision. So if the math is explaining to me why it's making certain decision, I can easily explain to my boss, this is why the model is leaning this way, and this is why the model is saying this or saying that. So, and then it becomes very easy. So you are not just struggling to explain now why the model has made this decision. You easily have it explained to you. So it kind of become really, really easy. And then fairness, it detects bias in data sets. So if a data is skewed to the right, it's going to tell you your data is skewed to the right. And that's why I mentioned earlier about feature engineering. So before you even get to AI and machine learning, those are the basics that you have to start with. So how skewed is my data set? Is my data it's my data set skewed to the left, or is my data set skewed to the right? And then robustness, right? So it helps you analyze sensitivity and stabilities. So again, it's important to understand the concepts and so forth. So what I would like to say before going to the math and going to our demo in VS Code and Streamlit is that you do not really need to be maybe a hardcore mathematician. I thought as but you have to understand the basics. You have to understand the basics. Especially linear algebra, you cannot do machine learning AI without understanding your matrices, without understanding your vectors, without understanding your scalars, your high dimensional tensors, and so forth. Because those will be the grounding boxes, and those are the terms you're going to hear all the time until you are done building all of your models. These are the things you'll hear. So you might not have a math degree like me, but you can still do AI and you can do better once you put your time to it. So first, you start with intuition and progressively deepen your math knowledge. So you start with you can go to Khan Academy. The first time I learned anything about data science, I started on Udemy. I paid for a course on Udemy with I forgot the tutor name, and he was really good. And he's patient. He will walk you through everything. So you start from the basis. You give yourself that grace to understand what's happening, and then once you understand what's happening, you are able to like, okay, let me start coding. So you understand the basis and then you start coding. What is the tool that you go to start? I started with Python, and I've become so biased. I work in Arrow, I work in C++, and then I work in Python, but I would never trade Python for any of those tools. Maybe Arrow next, I can stand C. But Python is my favorite because it's really, really easy to use and it's very, very intuitive. So it helps you build stronger principles. It helps you stay grounded. And the beautiful thing is, once you understand these concepts, you are able to freely walk into the machine learning world. You can build your AI models. You can build your deep neural network models, and you can do a lot of things. So I'm hoping that I can also get better at my math so I can specialize as a deep learning engineer before graduation. So now let's go to derivatives, the core math in machine learning itself. So derivatives and gradients, right? So you see the slope right here. That shows on our screen. So derivatives, in short, is a slope of a curve, which shows how fast something is changing. So in AI, derivatives or calculus, they just make it fancy sometimes to fear us. So in AI, derivatives tells us how the error's loss changes when we adjust a parameter. So when maybe you're trying to like carry on your gradient and you asking your gradient to adjust parameters. So the more you adjust your parameters, the more you are able to minimize your loss function in the right direction. So a gradient, on the other hand, is like a collection of derivatives. So when we have more than one parameter, so it just gradient just kind of like code on them and then train, learn and learn until it reaches the optimal point. So the way I would like to think of it, the way I would like to think of it is like an arrow pointing in the direction of the steep sets. So you have this arrow and then you use it in the opposite direction to reduce errors and then improve the model. Sorry, I got muted. So that's how our derivatives work in machine learning. And this is mostly required when you say you want to be a machine learning engineer, you have to understand your derivatives. You have to understand your gradients, how they are working, whether you want to do stochastic gradient descent modeling or you want to do gradient descent in general. You can easily get through it if you understand how they are working behind the scenes. So then we come to the chain rule. So the chain rule is important. I also learned the chain rule on the basic side when I was doing a course at MIT, but then I got a deeper understanding of what chain rule and backpropagation is and how important it is when I started my master's program. But for data science, for example, if you want to just be a data scientist, I'm sure you don't need all this heavy kind of math. But once you are going towards being an AI engineer or deep learning or machine learning engineer, you have to understand chain rule or backpropagation. So chain rule in calculus help us calculate how changes pass through multiple functions. So in deep learning, right, we use this in a process called, like I previously stated, backpropagation, where it allows the model to know how each layer contributed to the final error. So every layer can adjust itself correctly during training. So with backpropagation, you're like, oh, okay, now my person has this output and the error is huge and I cannot work with this error. It doesn't make sense. And maybe my prediction says 60% or 70% and my boss wants 90%. So once you pass the chain rule, your model backpropagates. It goes back to find what's happening with the error. And then it helps you to eliminate the error, adjust the model correctly until you have your desired output. And then the loss functions I stated previously We have different loss functions for different things, the loss measures between the truth and the predicted, the average square in regression category, cross entropy, and so forth. So once you understand your loss function as well, you're able to say, okay, I have a calendar problem. I cannot use MSE, mean square error or mean absolute error, because I'm not trying to predict the prices of used cars in the market. I'm not trying to predict the prices of cars in Boston or in Synco, or prices of houses in Synco or in Boston, or the future of these commodities. What I'm trying to do is to understand whether this person has cancer or no, whether this person is diagnosed with this disease or no. So with that, you cannot use MSE, right? We use functions like cross categorical entropy and so forth. In deep learning, we use like a sigmoid function. So it also depends on what use case you're working with. And then because gradient descent is one of the most important optimization tools, I would like to go over it again. For me, I always like going over the concept of gradient descent, because apart from understanding how important it was, I also usually like the way it sounds. So I used to be like, oh, gradient descent, gradient descent, gradient descent. But it's like rolling down a hill to find the lowest point in a valley. Let's say you're trying to take a walk and then you start to run. And then you can't be up that hill. You have to find a place where you stop. So if you're rolling down the hill and trying to find the lowest point in the valley, what the model is doing, it adjusts the parameter. So as a human being, you're going to be like step by step, moving from one direction to another, reducing the hill you're coming from, and then coming down to where you're supposed to be. So at first you start running, you get through, and then you reach at a certain place, and then you stop. You're like, okay, if I run too high, I will fall. So I'm going to take this step. I'm going to go step by step by step. And then the more you go, the more chances of your falling becomes small. So that's how gradient works in our model. So if you pass like a gradient descent optimizer to the model, it's going to take all features into consideration. It's going to start, and then it's going to go through each feature. It's going to optimize through each feature based on the learning rate that you pass. And then once it reaches the local minimum, you are able to say, okay, I'm at a point where I can accept this error. But if it reaches to a global minimum and you accept it, there might be something going on with your model. Either it's overfitting or underfitting, or something is happening. And then, okay, I just mentioned overfitting, underfitting. Now I gotta talk about how to deal with overfitting and underfitting. But let's finish with this first. So once you reach the local minimum, you are able to say, okay, this error is acceptable. So there are two different places you can reach with gradient descent. You either reach local minimum or global minimum. So global minimum is not capturing all your different data sets, all your different points, all your different features. But the local minimum is, okay, this is where I can stop. I know when I stop here, I am safe. And I know someone will see me and they're going to help me. That's what the model does. So it goes through all your parameters, reduces your error, it keeps adjusting, and it gives you your local minimum or your error rate. So this is so important to understand, because this is the main way AI models learn from data. This is the way it learns from data. So understanding your optimization techniques, again, it depends on what kind of technique you want to use and what kind of data sets that you have. Some people go with RLMS Pro, most of my professors prefer Adam and stuff. But for me, because I like the name gradient descent, so most times I maybe go with it. But then the learning rate, right? So the learning rate decides, like I said before, how big each step in the gradient descent is. So a small learning rate is slow but steady progress. A large learning rate is fast but risky. The model might overshoot and fail to learn. And then finding the right learning rate is critical for training success. So it's really important to know how you are defining your learning rate. So when I started coding, I used to be very impatient. So I'm like, oh my God, this is so why this model is taking so much time to learn. So what I would usually do, I would overshoot my learning rate because I wanted to go through fast. Like I would define my learning rate to maybe something 0.6 or 0.5. And then before I look, the model is done training. Okay. But this is not making any sense. The error rate is high. What am I doing? And the prediction is not worth it. So then I will have to like go back, adjust my learning rate for my model to take time how it's learning. And then eventually it's going to give me the output that I desire. So then activation functions. Once you start your machine learning and AI joining, these are the terms you will hear all through your life. I get tired with it almost all the time. So whether you are doing what's the thing name, large language models, NLP, CNNs, you're going to hear about artificial functions because they're telling you how where at what point the model should activate and on what stand it should activate. So activation function is giving our neural networks the ability to learn complex patterns, right? So like the sigmoid I emphasize first in mostly using deep learning application, kinds of like switches values between 0 and 1 and mostly used for probability. Is there a probability that this person has cancer or no, or they do not have cancer? And then the 10H similar but ranges from -1 to 1. And then we have the ReLU, which only keeps positive values, making training faster and efficient. So there are different types of learning artificial functions that can be used in machine learning. So, but one thing to understand is that without these activation functions, right, neural network will just behave like simple linear equations, and which is no use. So again, it depends the stage you want to go. So if you want to be maybe a ML engineer or deep learning engineer, you have to understand how these different activation functions work. And then we have the probability and Bayes theorem. So the Bayes theorem is so simple, but it's very important because it like lays the foundation. It shows you tells you how your data is evenly distributed, right? We previously talked about the binomial distribution, the normal distribution, and so forth. So when you visualize the data sets in Python, and you try to understand how your data set is distributed or how it's spread across its means and what is its standard deviation. So once you understand these concepts, you are also in a good space. So with probability, obviously you're going to learn AI will help you handle uncertainty, predicting whether it will rain today or it will rain tomorrow. So most times in the US, the people who use weather scientists mostly go with the different Bayes theorems, probabilities, and statistics to determine whether what the weather will be like today, or whether it's going to rain in Pinsfield tomorrow or rain like day after tomorrow. So the Bayes theorem, in essence, help us to update our beliefs, when new evidence comes in. So it's like adjusting the weather forecast when new satellite data arrives. So I'm going to adjust my prediction or my forecast for sink or rain tomorrow based on new data sets that I just got. And then neural network math, right? Let's talk about the neural network math or the file path. So a neural network usually takes inputs, multiplies them by weights, adds a bias, and passes the result through an activation function. So this is repeated layer by layer until the output is produced. So this is like simple math, right? Like multiplication plus addition plus activation, which allows network to solve complex problems. So again, depends on how far you want to go. These are some of the very key important math concepts you have to understand in machine learning, AI engineering, and data science. But if you just want to be a data scientist, I've met a couple of people with data science degrees that don't even know how to code in Python. They just use what's the database, the data tool name. They just use like not arrow, but
Cargo,
hmm?
cargo, cargo data sets.
No, not
SPSS.
Cargo. No, I'm talking about a database system. Okay, whatever. I forgot. So there are a lot of people who really don't know how to code in Python, and they are data scientists. So it depends. And then most times people ask us like, "Hey, you guys are learning so much at Harvard. I didn't learn this in my data science program." Yeah, but you cannot say schools like Harvard don't really care whether you want to be a data scientist or ML engineer or deep learning engineer. Is up to you. But they're going to give you all the required foundation that is necessary. So again, your derivatives and your gradients will show you how to change parameters, your chain rule propagation, go back propagation to update your error rates, and then your loss function, defining what wrong means, your activation functions, adding flexibility and non-linearity to the model, and then probability helps deal with uncertainty. So together, all these ideas coming together helps you form a strong mathematical backbone in AI and ML. So I would like us to go to so I did a okay, no, this is not it. I did a very quick bill for this season this morning. So I like us, let me just stop this one from running and rerun it for us to see how math in AI happen in real time, and that will be the close of my presentation. Okay, great. So this is a mathematics behind AI and ML, an interactive demo to see how math powers artificial intelligence, and then we have the same thing we're going over scalars, vectors, and the meaning, what it means, what it's telling us, and then the vector component A, vector component B, and so forth. And then we see calculus gradient, and we see the learning rate, how you adjust the learning rate, what steps the model should take, what's your initial point, and so forth. And then we see your different loss function, the steps that your gradient descent will take, and the steep flow until it reaches its local minimum. And then we see probability and statistics handling uncertainty in our data sets. And then we see the Bayes theorem, very simple theorem, but very, very important because the foundation of the concepts relies on understanding these things. And then the neural network math demo, and the different linear combination, ReLU activation function. So there's no time to go through all of them one at a time. Okay, this is the function, the formula for categorical cross entropy, the mean square error mean square error rates for regression models, and then the gradient descent. The formula I will never forget because I almost failed my first gradient descent exam, but I aced it at the end of the day. So gradient descent, where we just take our old weights, pass it on to the new weights, and then we minus our linear rates and then multiply by our derivatives term. So, ladies and gentlemen, this is all I have for you today. And thank you so much for listening. And I hope that taking your machine learning and AI joining, you can be very patient with yourself to go through the foundation and what is required. And I also, one professor who helped me a lot was Andrew NG on Coursera. I have so many certifications on the deeplearning.ai. So some of them I apply for scholarships on there, and they want people to learn, so they are very flexible with that. So I was able to learn all these concepts, and then by the time I started my master's program, I was like 3, 4, 5 steps ahead, or else I will be lagging behind. So give yourself the time, give yourself the patience, learn the foundations, and you'll do better. Thank you.
Okay, so give yourself the time, the patience, and everything, and you're gonna do better. And somebody said everything is simple to you. So I hope probably you was following the comment section. It was also interesting. And I think actually the participants really enjoyed the day. And thank you guys so much for availing yourself to be here. We really appreciate. Sorry, I wanted to take a screenshot of a screen that you just shared. Can you please reshare and just show the top of the graphical illustration thing you were just doing? I want to just.
Did you mean the one on Streamlit, the demo?
Yeah, the last one that was showing.
Okay.
Yeah, so
I can
guys,
also just send you the code.
No, I just want to get it while you are here. And
okay.
Yeah, I'll send you what I'm talking about. So while you are here, please send your best wishes and every other thing to our speaker for the presentation today. And I don't know if we have much time, but I would like for she and Tianyi to just have maybe, okay, right, the top one, just for the title, okay, right there, thank you. So Tianyi, are you there?
Yeah, I'm still here.
All right, so how can you relate this with your presentation, or what can you say about her presentation and what you also presented on, or probably what you are also still doing? Or what would be your advice to the participants that are following?
Well, I said in the chat.
Oh, okay.
Yeah,
I think
I said in the chat. Yeah, I said in the chat already that I'm so glad that I didn't talk anything about math and the technical aspects, because I didn't know that you were planning like a second talk which has all this information. So I'm glad I didn't, because it was all covered in Helen's great presentation. And maybe it was for some people who are not really into the math and the technical details, maybe it was a bit difficult. So maybe it's better to get first initial understanding from my overview, and then if you're interested, you can sort of take a deeper dive into the math. And yeah, I mean, if you're really interested, then you should really follow what Helen's doing and get that. I mean, I had to study that also in the beginning a lot, and then after you know the details, you can go up to abstraction and close to application. Or sometimes you can just do application, and you don't need to understand maybe so much about the details, unless you're really sort of curious and interested about that part. So it's all up to you, I guess. I mean, not you per se, but the general you as a student. Yeah. Thank you.
All right. Okay, thank you so much. Helen, is there anything last from your end? I think we have two-person hands up.
I think there are questions.
Okay, let's take Collins, and then after we take Elijah, while I'm trying to find the comment section for questions. Collins,
Thank you, CEO. Thank you, CEO. Very thank you to Miss Helen for clear insight about the math behind deep learning and AI, especially for data scientists and those who are into machine learning. Yeah. I want to know the difference between the explainable AI from confusion matrix. That is one question. And second question, please, looking at the math, the concept about math behind this AI and data science is very clear, and everyone needs to know the foundation and everything. But my problem is there are some series of resources that I usually follow, especially on YouTube and other Coursera platform and Kaggle. When they want to build a project, like maybe classification of dogs and cats, or maybe cancer or not cancer, diabetes, when looking at their codes, right types, their scripts, it's like they just load the data, they pre-process it, they scale and they split the data and the test and training, then they feed to the machine. Then the machine will do its tasks. Then finally, you just predict the results, like the accuracy, the percentage. Then if there is any loss function and that stuff, you just prompt the machine with some parameters, then it gives It refine the loss functions or correct the losses. All these things that I've been watching on the resources, Kaggle and other platforms, it's like all these math details are not being manually calculated by the user or the programmer. You understand? But then there is a math behind, and I want to know that is it compulsory to know the math behind, or we are the programmer or the user would manually calculate this thing when you are maybe building a project or building a project. I want to know.
Okay.
That is the thing.
Yeah, Colin. So, to answer this question, then the first question, so we do not manually calculate what's happening, right? The machine does it for us, but you will not know what's happening if you do not understand what the machine is doing at the back.
Okay.
Yes, so that's why it's important to know the math. You're not going to say, okay, I'm about to calculate the gradient. But if you know how the gradient is calculated, you will understand what's happening behind the hood.
Oh,
If you
okay.
understand, like, for example, matrix multiplication, right? You understand how your data set is being transformed. So having the basics will really get you understanding what's going on. That way, if you
Behind
encounter error, yeah, if you encounter error, you can say, okay, no, 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 something is going on. Maybe I'm missing something. So it helps with
Sure.
intuition. Yeah.
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 Okay.
So the machine does it, but it's quite important to understand what the machine is doing.
Okay. What about the explainable AI, the
Yes.
sharp and the lime and the
And
confusion matrix?
confusion matrix, right?
Mm,
So
mm,
confusion matrix is like a table, right? That will tell us
mm,
how well a classification model is performing. So classification
mm,
models give us binary prediction. So it helps us measure accuracy and error. So for
mm.
binary classification, right? When we do binary classification, we want to know our true positives, our false positives, our
Opposite.
true negatives, and our false negatives. Because
Mm,
sometimes the model overfit. And then when the model overfit, if something is true positives, it tells you it is false positive. If something is false
mm.
positives, it tells you no, it's
So
false
this is
negative.
opposite.
So
Mm,
that's why it's called confusion matrix. But it's a table that's telling you how many true positives we have and how many false positives, and which ones are indeed true positives, but the model is telling us they are false positives.
mm, mm, mm.
So
Oh,
so it's like calculating accuracy, right? Where we calculate precision, recall, F1 score, where
Mm,
it all boils down to telling us where the model is making mistakes. So you know this
mm.
is supposed to be true positive, but the model is telling you this is false positives. So now
Okay.
confusion, yes, that's how it is. Now confusion matrix is telling you this is where the model is making the mistake.
Mistakes.
Because
Oh,
then you
okay.
get confused. Like if you manually tune in, you straining your brain like, this is true positive. Why is it false positive? And then confusion matrix explains to you where the model is making mistake.
Oh, okay. Okay.
So in a medical
Explainable.
setting, for example, right? If
Mm,
someone conducts a medical test, sometimes they comes by tell you say, for example, you were HIV positive. You say, no, 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 I'm not HIV positive. This is a lie. So the model
mm.
there is incorrectly giving you
Prediction.
prediction that
Yeah.
yeah,
Ability.
that does not belong to you. So the confusion
Mm,
matrix tells the doctor where the model is failing. So it shows how
mm,
many patients, then sometimes what the doctors will do, they go back to see how many patients were correctly or incorrectly diagnosed, and then it makes some adjustments based on the
mm.
results. So then it goes back and reads your test, and then you like come by and say, oh no, that was a mistake, sir, I'm sorry.
Okay. Okay. Well
Yes.
so
understood.
lastly,
Well
let us
understood.
take
Thank
Elijah.
you. Yeah.
Then the question
And
with
the
explainable
explainable.
AI.
Yeah.
So explainable AI is like basically just broad sets of techniques, right, that help AI make transparent and that help AI to be more transparent and interpretable to human beings. So like CEOs, right, like managers who are
Mm,
not data scientists or ML engineers, if you work in Silicon Valley, most of these
mm,
millionaires or tech start companies, their CEOs do not understand what is happening with the
understand.
AI.
Yeah.
So if you are not in a position where you can technically explain, because some people
Explain.
understand what they're seeing, but they cannot really explain it. Explainable
Mm,
AI will tell you, it's going to show you like features that is contributing to prediction. For example, what is driving rent prices in Monrovia, in Cinco, right? So you'll say
Mm.
convenience, 24-hour electricity, and blah blah blah. But what is the main thing? What are the main things? So if there are three main things, explainable AI will tell you these are the three main things that are pointing prediction.
Mm, mm, mm.
Yes, and
Well
then
understood.
LAM is also like an explainable AI technique, but that is like build simple interpretable models, right, around individual
Mm.
predictions. So it also boils down to telling you what feature have the most impact on certain thing. So if
Oh,
you where
okay.
you live, you know they have like middle class community and rich communities. What features make these community and rich communities? There are certain things where the person has to have six or seven figure job. They have to be in the certain category, they got access to this, they got access to that. So these are things that are
मार्केटिंग
causing a
प्लान
high
होता
practice in
प्रमोशन था
certain
ना
areas.
डिफरेंट पढ़ाई कर मैंने ट्रेड सर मैंने पढ़ाई कर बता
Understood.
And then, yes, and then you also see features that contribute to like maybe teenage pregnancy. So if you're modeling teenage pregnancy in Monrovia or in a
Rental
small
attendance
town,
will be taken.
Nigeria, there are features that will tell you what constitutes teenage pregnancy in these settings. So you'll see poverty,
Mm.
right? You will see hunger, you
Yeah,
will see different
yeah.
factors, but then it will suggest
Ethnic,
sometimes the three
ethnicity.
key important features that are increasing high rate of teenage pregnancy around the world or in your location you're trying to
Okay.
model.
Okay. Thank you very much, madam. I will
Very
get your
welcome.
contact so that I'll
Yeah,
learn more
sure,
from
no
you.
problem.
Thank you.
Okay, so Elijah, you can quickly pose your question or suggestion or comment, whatever you have.
Okay, I would like to say thanks to the two presenters for today's presentation. So I have two questions, right? And my first question is that how do we prepare and clean data for machine learning models?
So there are a couple of ways to prepare and clean data for machine learning models. So one is visualization techniques. So you can collect your data sets. You get raw data sets. You got they are in CSV files, they are in databases, they are in APIs, etc. Right? And then you ask yourself, you say, are there missing values in my data sets? And then you find the missing values from your data sets. And then you look at it, you say, there are too many missing values. What do I do? Do I handle them? Do I use so if you're dealing with numerical data set, you use your mean model to replace your most missing data sets. If it is mode, if it is categorical data sets, you use your mode. If it is advanced data set, use KNN regression, etc. So first you visualize your model, you go into the cleaning process, and then that's what they call feature engineering as well. So you've already seen whether you got duplicates, whether you want to remove them, whether you got fixed data type, whether you got outliers where you can see them using visualization like box plots, histograms, and so forth, whether you have whether you need to kill your values, because if you have like yes or no, or if you have drawing cat in machine learning, you can't put drawing cat no matter, you have to like scale them, or you have to normalize them or standardize them to a mean of 0 and standard deviation of 1. So it's either 0 or 1 that is going to give you an output. So you go through the entire process of visualizing your data using different charts for different scenarios, and then you handle missing values, and then you drop duplicates. When you've done all of those things and you feature engineer, what is the most correlated features, what are the most duplicate features, and what are the outliers? And once you've done feature engineering your data sets, you can go ahead to start modeling. But there are different steps to cleaning one's data sets before machine learning, before building your model. But the
Okay.
main one is understanding your data, and that starts with visualization. Visualize the whole thing. Understand your summary statistics. What is your mean? What is the variance? What is the standard deviation? Things like that.
Okay, thank you. Then my second question says that why do deep learning models need so much data and computing powers?
Because they are heavy, right? So machine learning, traditional machine learning, we're talking about regression. My boss, I work for a real estate company. They want to know the future of housing in Boston or in Washington, D.C. That's not very heavy. But if I start working for Tesla, Elon Musk wants to know how his CNN algorithms will work, how his self-driving cars will see red light and stop, how the
Okay.
self-driving cars will go to where will automatically drive someone else when it's just programmed. And then natural language processing. We take words like unfiltered data sets, huge texts of data, and then we train Siri. I want when I say anything to Siri, no matter what accent I'm saying it in, Siri should understand. So the data sets can be so heavy. It can be very, 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 very heavy. It can be way bigger than that traditional machine learning models. So that's why it becomes computationally expensive to train them. That's why I think it's called deep learning. Because at this point, these things are mimicking the way the human brains work. That's what deep learning does. It mimics, their point is to make the way you and myself think. If I'm driving a car and I'm supposed to stop at Cinco, I know I'm going to 12th Street, I will stop in 12th Street. So deep
Yes.
learning is training this car to also stop at 12th Street when you reach there. So it's acting like a human being. It's mimicking the way I drive.
Okay.
Yes. So that's how powerful deep learning models are. And that's why they are very computationally expensive. They are
Okay.
far from regular machine learning models like regression, classification, those kind of stuff.
Okay, thank you. Thank you very much for that. And my last question says that I say, yes, I said, how does a backpropagation work within training neural networks?
Okay, so backpropagation, right? Let's say you finish training your model, okay? You've reached a prediction, and your model is giving you maybe 60% accuracy. And then you're asking yourself, what happened to the 40%? What's going on? So you initialize your backpropagation technique. Backpropagation will go back to adjust every error. Like it will find where the error is coming from, adjust those parameters, and then come back and give you a better output. So backpropagation happens when you already have your prediction and you're trying to go back to see where your errors came from and how you can minimize those errors. So backpropagation happens when you are done getting your prediction for a certain model or for a certain problem.
Okay. Thank you very much. Thank you. I
Very
understand.
welcome.
Yeah,
Yes.
thank you.
Very welcome.
All right. Okay. So officially we have 7 to 8 minutes. And the next thing we should be doing is our attendance. But I think we can give.
I see Lloyd has a question.
Okay, Lloyd, you can go ahead. Lloyd Pee-wee.
The last person.
Okay. Yeah, I'm so lucky to be the last. All right. Thank you so much. I highly appreciate the both speakers. You guys really did well. My question is just almost like the second to the last response you did as it relates to machine learning. I'm a student from the civil engineering background, and my research currently I am like building a model, a pavement model, because I'm specializing in pavement designs and mechanics. And I'm using the finite element analysis software, which is called Abacus. But then after simulations, I'm supposed to use the achieved data and build a predictive Decatur twin model that will explain the behavior of pavement under dynamic vehicle loads. But then I need the aid of either deep learning or machine learning. But I think from what I'm learning from you tonight, machine learning has a lot of possibilities. So my question is like, from your own expertise as it relates to working with machine learning in building models, especially where I'll be deriving both view of how you call it, vertical and that of the temperature data. What method or which of the various kinds of machine learning, especially as it relates to the various algorithms and what have you, do you think you can recommend that I can quickly focus on, because I'm not too good and I've not been really working with machine learning, honestly. So I need to put in time, maybe in the next 3 to 4 months, that will be able to achieve what I need to do, especially having gotten my data that I can be able to implement machine learning to build this digital twin model? That's my
Okay,
question.
did you say temperature data?
The pavement is a combined both dynamic, that is vehicle load, and temperature load. Is a mix, is a doubled data. Like when car is moving on the asphalt pavement, let's assume during winter, right? So let's assume the temperature at that time was -15, and then the car is moving at 90 kilometer per hour, which is 25 meter per second. So the abacus software going to simulate and determine all of the time, they call it the moving time, and that of we have something again they call the temperature effect. So Abaku is going to determine all of those data, right? But I need to use the data to produce a predictive digital twin. Let's assume that maybe in the
Yeah,
next picture,
I think I understand what you're trying to say.
wants to build a
Okay.
road in. Yeah, so how
So
can I relate?
you want to understand the deep learning algorithms in that
Yeah,
area, right?
which of the deep learning I can use to build this digital twin from your own
Yeah,
expertise?
so for that use case, I would recommend RNNs, which are recurrent neural network. So the reason is recurrent neural network handles sequential data. So it learns like short-term dependencies between temperature fluctuations and vehicle load stress. So it predicts failure, it predicts couple of other vehicle load stress related activities. And then another thing I would recommend is LSTM, like lost long short-term memory, and GRU. So this is important because it captures long-term seasonal patterns and then it lack effects. So usually most times it's are due when low effects depend not only on like the current temperature of vehicle load, but also on cumulative exposure like heat stress, repeated heavy loads, etc. And then CNNs for time series. So which number three CNNs from time series, which treat temperature plus low as parallel sequence channels. So it extract low patterns and then it adds the spike plus the heavy low on a bridge, and then it helps you gather or share variation of what's happening. So for example, it detects anomalies like overheating engines under cargo weights, etc. Those kind of stuff. And then another thing you can work with are transformers. I don't know how much transformers will work in this case, but I'm sure attention models also handle multivariate time series extremely well. So you use usually in deep learning, we use attention to weigh which factor or which load or temperature matters most at each time. So example, like we're predicting flea wire maintenance needs, considering hot climate zones versus colder ones or snowy ones, etc., etc. And then another algorithm you can look at is a multimodal deep learning. So for example, right, if a vehicle load like comes from sensors, and accelerators, strange gadgets, and etc., what you can do, um, you can use multi-models to model and combine the structured data, the different time series data, and even images. So you are like predicting fuel efficiency, drop, using both sensors readings and environmental data. You can also use autoencoders. You can use physics-informed neural networks. I don't know a lot of people are aware about physics-informed neural network. Those can also be used for your case studies.
Okay. Thank you so much. It was great having you here with us, and we highly appreciate. We will keep in touch for
Yeah,
those that.
sure, anytime, definitely.
All right. Okay, thank you. So guys, please turn on your camera so that we can do the attendance, and if time permits, then we will probably take additional discussion if any. So please turn on your camera. We have officially 1 minute. I tried to do the attendance while the questions were going on. But then I'm also going to do this one. So if you observe the records for today, it's going to be probably, you might find some repeated screens. That's because some people were saying they have pin errors, they have data issue and all of that. So we just try to help them. Okay, I'm taking the first screen. I think everyone is set. So tomorrow it is 5. We will start the process of generating your certificates. Please don't send any message now. You're going to block somebody's face or their name. Just wait for the next few minutes so that we can get done with this. As always, some people.
I think my camera has been
Okay,
disabled.
I'm coming. It's okay, no problem. Just leave it. It's okay. If you can't turn it on, that's not a problem. So,
Okay.
all right. So please check the YouTube video first, and also check the PDF to know about your attendance before you can start to message us. If you can find it on the YouTube, it's also fine. If you cannot find it in a PDF, if you cannot find it on both, that means there was a problem. And that problem is from you, because we did both the PDF and it's also on YouTube. So I have 2 more slides to go. Just bear with me and let's get it done. Tomorrow is day 5. We should be having 2 speakers. So we will cross-check with them once more to know if they will be available for tomorrow. And anything we'll let you know, as always in our write-ups. We'll let you know. So just stay with me. I have 1 more. We're going to also ask the speakers for their slides. If they can provide it, that's fine. If they can, we'll advise you to just watch the video on YouTube in case you are missing on anything. And also their contacts, we'll also ask them for it. If they can also provide their contacts, we'll also share with you. If they cannot provide it, that's also fine. You can search for them on LinkedIn and other places. So I think officially I'm done with it. Let me just go through the thing for the YouTube just once more. So that's 1, 2, then 3, 4, 5, 6, 7, 8 different screens. So that's it. Thank you so much for today. Thank you for being here. We look forward to seeing you tomorrow. If your attendance record is not straight yet, you have missed probably 1 or 2 days, then you want to make sure that you are also in attendance tomorrow. So that is in effect. There was a guy who was just using Techno, and I think Teresa kept reminding him and other volunteers, but he just couldn't listen. And you will have these people saying, oh, I was there, but then how do we know you were actually the one using the Techno? But that's it. The videos will be on YouTube in a few hours.